This video is going to be part C of our probability series of lessons. And if you could please, at the top, make sure that you're using a pencil and then go ahead and write in the learning target. I can find the probability of independent and dependent events. So we're going to expand on probability, the things that we've been talking about, and we're going to get into independent events and what those are and how to solve for the probability when we have independent events as well as dependent events. So two events are independent if the occurrence of one event does not affect the occurrence of the other. And then two events are dependent events if one event does affect the occurrence of another. And so that kind of leads us into this idea of conditional probability, because if we do something, it could change the probability of the next thing happening. So the probability that event B occurs, given that A has already occurred, is called the conditional probability, meaning that something had to happen before the second event takes place. So this is how we write that in notation form, the probability of B given A. So this line between the B and the A is just the word given. Probability of B given A. And for example number 1, we want to identify independent and dependent events and then also solve for the probability. So a drawer contains 6 red markers and 4 blue markers. So we already have seen what we're dealing with, 6 red and 4 blue. If you randomly choose a marker from the drawer and do not put it back, then you are going to randomly choose another marker. What is the probability? Is it independent or dependent when you're just pulling a marker from a drawer? Well, the first time you draw is going to be completely independent, right? Independent meaning that it's not affecting anything else. It's because it's the first time you're drawing something out of the drawer. Now, what is the probability that the first marker you choose is blue? Well, how many markers are there in total? We have 6 plus 4, which equals 10, and 4 of them are blue. So 4 out of 10, or we can reduce that to 2/5. Now, event B taking place could be changed if we do not replace it. Now, we are not putting that first blue marker back in the drawer. So we've reduced the number of blue markers to 3, and we've also reduced our overall total number of markers in the drawer. So this one is going to be considered dependent. And the reason it's dependent is because the first time we took a marker out, we did not put it back. So those are some key words that you're going to want to look for when you're solving these types of problems. If you did not put that first item back, whatever it might be, then the second probability is going to be altered because of that. So we have less markers in the drawer. We only have 9 markers in the drawer. And remember, one of the blue markers got taken out, so now we only have 3 markers that are blue left in the drawer. And we can reduce that. So the chance that we get a blue marker the second time is only 1 out of 3. The first time we were drawing from the group of 10, we had a 2 out of 5 chance of pulling a blue marker. So I hope this helps you see the difference between independent and dependent events. And when you're working on the practice problem, make sure that you're thinking about whether you are replacing it or not replacing it. So let's read through that question real quick. It says a bucket contains 4 tulip bulbs and 3 daffodil bulbs. You randomly choose a bulb, you plant it, and then you choose another bulb. So is the first event independent or dependent? And is the second event, event B, dependent or independent? If you plant it, then are you putting it back in the bucket? Probably not, right? So you're planting it and you're not replacing it. So just remember, when you're not replacing something, that's going to change the total number of bulbs in the bucket. All right, and let's go ahead and look at example number 2, where we're going to find probability of independent events. And these are events that do not affect any other events taking place or any probabilities at all. So this is our formula, probability of A times the probability of B. That's going to be, what is the probability of both of these things occurring. So that's the probability of both, A and B. All right, if we look at the problem, Kanisha and Ramon each have a standard deck of 52 cards. And we're familiar with that because we've worked with a standard deck of 52 cards, and each one of them separately has their own deck of cards. Each one draws a card at random from his or her deck, and we want to find the probability that Kanisha draws a heart. Okay, so what's the probability that Kanisha draws a heart and Ramon draws a 6? All right, and so we're going to say that this is the probability of A taking place, and this is the probability of B taking place. And according to our formula, we just need to find those probabilities and multiply them together. So if we recall from the deck of cards, there are 13 hearts out of 52. And if we reduce that, the probability of Kanisha drawing a heart is 1 out of 4 because there are 4 suits. And then Ramon drawing a 6, there's a less chance of him drawing a 6 because there are only 4 out of the 52 cards that have a 6 on them. And if we reduce that, he has a 1 in 13 chance of drawing a 6. So over here, we're just going to multiply the two probabilities together. The probability of A times the probability of B, and that's going to give us the probability of both people drawing those specific cards out. And now if we take our calculator and divide 52 into 1, so just type in 1 divided by 52, that's going to equal 0.019, or in other words, it's a 1.9% chance that Kanisha will draw a heart and Ramon will draw a 6. All right, using the information that you just learned in example 2, please try the on your own practice problem. And this one is where you have 3 red sweaters, 2 black sweaters, and 4 gray sweaters. You randomly pick one sweater and then you put it back. Okay, so if you do put it back, is that going to change the probability when you draw a second sweater? So you have to think about that and then just, of course, use your judgment and try to find a reasonable solution to that problem. And then at the bottom of the page, we have example 3. We're going to find the probability of dependent events. And sometimes with these problems, you're going to see the words not replaced. And if something is not replaced, then that's going to change the probability for the second time something happens. And if it does not say this, then you need to read into the problem a little bit more and find out if maybe it didn't get replaced, but it didn't specifically say that. And let's take a look at this problem and you'll know what I mean. So finding the probability of dependent events, this example says that there's a bucket that contains 40 yellow golf balls and 30 white golf balls. And you randomly choose a ball, and then you hit it toward the flag. Okay, so there's a flag out on the golf range, and you hit that first ball toward the flag, and then you randomly choose another ball. Well, it looks like to me then, just from reading what it says here, the first ball is not replaced. So we need to find the probability that the first ball is white and the second ball is yellow. All right, so what's the probability of us pulling out a white ball first in the bucket of 70? All right, I know I have 70 total because there were 40 yellow and 30 white. So the probability of white is going to be 30 out of 70. There was no, that's the first time we pulled a ball out of the bucket, and so we don't have to worry about it being dependent or independent because it's the first time it's happening. But the second time we go to pull a ball out, what's the probability that the second ball is yellow, given that we already took a white one out of the bucket? Okay, how many balls do we have left in the bucket if one got hit toward the flag? That first white ball got hit toward the flag, and now there are only 69 balls left in the bucket. And how many of them are yellow? Well, there are 40 yellow balls left in the bucket. And we're looking for a joint or both kind of answer here. So the word and means that we're going to multiply. So rather than using 30 over 7, 30 over 70, I'm going to use 3 over 7 because I know I can reduce that and use the smaller numbers, which are easier. And then I'm going to multiply that by this second probability. So the first probability was pulling a white ball out of the bucket, and then the second probability is pulling a yellow ball after a white ball has already been taken out. And if I write this down, I did 3 times 40. Remember, when you're multiplying, you're just multiplying across the top. You don't have to have the same denominator or anything. So multiply 7 times 69, and we get 483. And if we punch this into our calculator, 120 divided by 483 is 0.248. So we have a 24, almost a 25% chance of pulling a white ball first and then a yellow ball after we hit that first white ball toward the flag. And on the back side of the paper, we do have the on your own practice problem where you have 10 peaches and 8 nectarines in a bowl, and you randomly choose a piece of fruit and then you eat it, and then you randomly choose another one. So using the previous example that I gave, please try to find out if you are going to need to alter your probability based on the fact that you ate that fruit. Did you put it back in the bowl? So you have to make that decision and then calculate accordingly. We are going to take a look at example 4, find a conditional probability. What does it mean to be conditional? Well, conditional just means that you meet a condition. Okay, so you're looking for which condition do I have to meet in order to calculate this probability, or which condition does this item have to meet in order for me to calculate it correctly. So if we take a look at this table, how many seniors and how many juniors do we have total? This table shows us that we have different window treatments on bedrooms in these different students' homes. So if I add this up, I have a total of 67 students that have blinds. Okay, so between the juniors and the seniors, there are 41 juniors and 26 seniors that have blinds. So just make sure you're looking at this correctly. 180 students have shades on their windows, and if I add this up, it is 61 people between the juniors and the seniors that have curtains. Now, this isn't Centerline High School or anything like that. Well, I don't think it is anyways. This just is a little table that was given to us. How many juniors are there in total? Well, that would be us adding this direction, right? We're going to add up all the juniors, 162, and then add up all of the seniors, and that's 146 seniors in total. All right, that's like the total column there. All right, so our task is to use the table to estimate the probability that a randomly chosen junior, okay, so here's the condition. First of all, the student has to be a junior. So we're looking for that condition. And they also have to have blinds in his or her room. All right, so how many students that are juniors? Well, you first have to be a junior. And then you have to have blinds. All right, so the people who are juniors, there's 162 of them. And if you have blinds, that's 41 out of the 162. So if I use my calculator and get a decimal answer, it's 0.253, or a percentage answer is 25.3% of the people that are juniors have blinds on their windows. And the part B of this problem says, what is the probability that a student who has blinds? Okay, so now we're changing it so that the condition is that you have to have blinds. Well, everybody in this row has blinds, so that's a total of 67 students. 67 students have blinds, and they have to be a junior. So I've switched the letters here. This one we said if you're a junior, then you have blinds. This one is if you have blinds and you're a junior. So there are 41 people of the people that have blinds who are juniors. And now I can take my calculator out. 41 divided by 67 is 0.612, or 61.2% of people who have blinds are juniors. So more than half of the people that do have blinds are people in the junior class. And then over here, we switched this slightly. The first time was that you had to be a junior and you had to have blinds. So the condition is the first thing listed there, and then there's a second condition that you either have blinds, shades, or curtains. Now, when you go to do your on your own practice problem, you're going to still use this same table, but this time you're answering this question and this question. Now we are going to do example 5 in class and the practice problem that follows. It's a little bit extensive for this video, so I'd like to just do that in class with you. And if you have any questions about any of these other examples that I've shown here, or about independent and dependent events, please make sure you ask in class. Thanks a lot for watching.